Okay, so I've received a couple of emails either from you or from parents, guardians asking about the SUNY Schenectady bill. As far as I know, your certificates of residency, for those of you who are not Schenectady County, they were submitted. So sometimes it takes them a little while to get everything synced up. If you have questions about your bill or how to pay it, they're not going to tack on a late fee if it wasn't paid. They're not dropping you from the course if it wasn't paid. I think they said the email I received said payments were due November 3rd, which was yesterday. If it wasn't paid, don't worry about it. They're not dropping you from the course. They're not tacking on a late fee. Just give them a call at 381-1346, or you can email bursar@suny.scccc.edu. The bursar is the one who handles all the billing stuff. All right. So if you have questions about anything there, you can give them a call to ask about your bill and how to pay it. I don't know if they have online payment or not. That is something to ask them. I just teach the course. That's it. That's my job. My job is to teach it and put in a final grade for you in June, and that's it. Okay. So anything else you have to deal with them about. But that's another phone number from the college and the high school department. They said they actually don't handle the billing either. The woman who directs, Susan Neary, who's director of the college and the high school program there, she said she has nothing to do with the bills. So you have to talk to the bursar, which is typically how colleges do it. All billing is handled through the bursar's office at a college. So that's the phone number for the bursar if you need it. Okay, let's check your answers to the evens. You've already done the odd problems. Check them in the back. The only even one I have to give you is number 70. Is that correct? Yeah, 70. Okay, the answer for R, algebraically, the answer for R, the expression you should have derived should have looked like this. It should have looked like M2G capital T squared over M1 times 4 pi squared. Remember, anything in the numerator can be in any order because it's multiplication, but that's the final answer for R with those variables in the top, those variables in the bottom, and that's it. All right, do you guys want to go over anything? Ruben, you got it. Let's look at 65 first. All right, 65 says that we have a stone that's that has a mass of 95 grams being whirled in a horizontal circle on the end of a string that's 85 centimeters long. The length of time required for the stone to make one complete revolution is 1.22 seconds. What angle is the string making with the horizontal? All right, so this is a lot like what you were doing in the last lab. Just had all this paper here, and now I've lost it. There it is. With the bat flying in the circle, it doesn't fly in a perfectly horizontal circle. The tension makes an angle with the horizontal. So this is really what you've got here. Here is the stone, it's at some tension point here, and we know that the length of the string from here to here is 85 centimeters. I'm going to break this into components. This is the angle that you're looking for. What is this angle here? I'm going to say that side of the triangle is the radius of the circle that it's moving in. 85 centimeters is not the radius of the circle. Okay, because if it's going in a horizontal circle, that distance, which would also be here, is the radius of the circle. Now, if I were to draw a free body diagram for that stone right there at that point, I would have a tension force pulling up and left, and the only other force that's acting on it is the force of gravity. We know that when something moves in a circular path at a constant speed, that the acceleration is directed directly towards the center of the circle. So the acceleration in this problem is to the left at this point in the circle, which means that I need all my forces to be resolved into the perpendicular direction of the acceleration and the horizontal direction, which is parallel to the acceleration, which means we would resolve that tension force into a vertical component and a horizontal component. The weight would remain because it's already along one of those axes. Now, since the stone does not accelerate vertically, it means that the y component of tension is balancing the weight, and the net force acting on the stone in the centripetal direction is FTX, is the x component of the tension, just like with the back going in the circle. It was only the horizontal component of the tension which provided the centripetal force. So the first thing I'm going to do in this problem is figure out what speed that stone is moving in by using our equation for speed in a circle, circumference over period. And I'm going to do that so that way I can come up with an equation for this where I know that R, if I look at where R is related to this 85 centimeters and that angle. It's adjacent to the angle, which means R would be 0.85 meters times the cosine of the angle. And the period I know is 1.22 seconds. I'm just going to leave that as my equation for the speed. Now, the second thing I'm going to do is look at that net force. The net force in a circular path is also called centripetal force. I don't care if you call it centripetal force or not. You can just call it net force for all I care, which means that that's equal to the mass times the acceleration, which is pointing inward in the horizontal direction. Now, how are we going to get that acceleration? We should know how to get the acceleration when you're moving at a constant speed in a circular path. That acceleration is the same thing as the speed squared over the radius. So that would mean I'm going to take the mass, which is 0.095 kilograms. I'm going to multiply it by this equation for the speed, which is 2 pi times 0.85 meters times the cosine of the angle, all over 1.22 seconds. That has to get, I'm running out of room, squared. And then I'm going to divide it by the radius one more time, which is 0.85 meters times the cosine of the angle. Right? Because that's V squared over R. Now, I'm not solving that yet. How do I get that net force? I'm going to get it by understanding now that in the y direction, that the y component of tension is balancing the weight, which means that the y component is just m times g, which is 0.095 kilograms times 9.8 meter per second squared. But the y component of tension is related to that angle. It's opposite that angle, which means this would be the same thing as Ft times the sine of the angle. Are you with me on that? Yes? Okay. So here's what I'm going to do. This is the same thing as the x component of tension. That x component of tension is the same thing as Ft cosine of theta. So let me just solve this for Ft, which means that Ft would be 0.095 kilograms times 9.8 meter per second squared divided by the sine of the angle. And then what I can do is plug that in there. So look at what happens. That means I have 0.095 kilograms times 9.8 meter per second squared all over the sine of the angle times the cosine of the angle. That is my Ft now. This is Ft times the cosine of the angle. That's going to equal 0.095 kilograms times the quantity 2 pi times 0.85 meters times the cosine of the angle all over 1.22 seconds. This gets squared, and then we divide by 0.85 meters times the cosine of the angle. So notice that a bunch of stuff now is going to start canceling out, namely the mass, right? Okay. Now, I've got a cosine. If I were to square this out, that would be cosine squared over cosine. So what happens to those cosine squareds? This will cancel one of those, but then this is also going to cancel the other one. So the cosine term is gone completely, which means that I'm left with 9.8 over the sine of the angle equaling 2 pi times only 1.85 meter, right? Because that 0.85 is going to get squared divided by this. So one of them is going to cancel. This 2 pi is not. That's going to have to keep the square. And the 1.22 is going to have to get squared. Can we solve that for the angle now? Should be pretty easy to solve that for the angle. So if we do that, I'm going to get that the angle, well, let me do all of the algebra to make sure that we're all on the same page. So this would be 9.8 times 1.22 squared is equal to the quantity 2 pi squared times 0.85 times the sine of the angle. So that means the angle is going to be the inverse sine of 9.8 times 1.22 squared all over the quantity 2 pi, which must get squared, and 0.85. So now you're going to go to your calculator, make sure you're in the degree mode since all the answers are in degrees, and we're going to work that out. So 9.8 times 1.22 squared divided by the quantity 2 pi, which has to get squared, divided by 0.85. And now I'm going to take the second sign, second answer. That gives me 25.8 degrees for the angle, which means that the best choice is choice C, which is 26 degrees. Okay? So there's a lot of algebra. Because the x component, if I were to break this up, the y component would be here. The x component would be here. So if I were to move them here, here would be the y, head to tail. There would be the x. The x side is adjacent to the angle. Adjacent is cosine. If I move them head to tail here, FTY, FTX, there's FT, there's the angle. They want the angle with the horizontal. So FTX would be FT times the cosine of that angle. Okay. So I'm trying to keep everything in terms of angles and trying to get rid of things that aren't. No. So over here, to get the y component, I know the y component would have to be FT sine theta. And the x would have to be FT cosine theta. Just breaking that up into components. So that's why I'm changing FTX into FT cosine theta and FTY into FT sine theta. Okay. You might get a slightly different answer, but they only had it with 2 sig figs, 26 degrees. Usually what we want you to do at the AP course is save all of your calculator work till the very, 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 very last step. I'm telling you what we expect at the AP level. So if you're doing things differently than that, and you end up with slightly different answers, you're expecting the person who's grading your paper to do all the calculator work in between. They're not going to do that. So when we grade AP tests, I'm going to tell you, I'll tell you how we get paid. There's an hourly rate, and we get bonuses if we grade a certain number of papers per hour. We are typically told to spend no more than 2 minutes grading one person's response to something, to a 15-point question. We have 2 minutes to grade it. If it's taking us longer than that, we're told, don't try to figure out what they wrote. If you can't follow it, it's wrong. And we just start deducting points. So not only does your penmanship have to be good, but your logic has to be clear. That's what happens in the scientific community. You publish a journal. Do you think people are going to scratch their head trying to figure out what the heck you did? No. They're going to say, if they can't follow it, you're not explaining it in a way that makes sense. So I'm telling you, save all your calculator work to the very last step. I'm going to tell you on the AP test in May, it's not going to be a problem because you're probably not going to need a calculator for anything on part 2 of the test. It's all algebraic. So you got to get really good at understanding how to derive equations just using variable letters. Just using letters. Forget this. Throw it out the window. You're not really going to need it. I'll tell you, prior to 10 years ago, kids were not allowed calculators on the AP Physics test anyway. Now they're giving it to you. But do you really need it? No. Okay, so I want you to really try to do everything algebraically first. If you do that, you're making your score in May higher because you're getting more practice doing algebra. Heck, you guys are in AP Calculus. Algebra should be like a no-brainer. Yeah, it's long and it's complicated, but get over yourselves. Just because you're an AP Calculus student doesn't mean you're good at algebra. We got to get you good at algebra. Algebra. Algebra 1 is what we're doing here. So go back to basics. You should be able to do the algebraic manipulation and derivations. All right. Anything else you want to ask? 67, part C. Anyone need part A or B to 67? Yes, both parts? Okay, so let's do all of 67 then. Part B, okay. We're just going to do the whole thing. So in 67, it says we have a 0.75 kilogram stone, which is attached to a string, which is whirled in a horizontal circle of radius 35 centimeters, as in the conical pendulum of example 5.9. So hopefully you went back in the text and you looked at example 5.9 in the text because they basically showed you how the problem works. The string is making an angle of 30 degrees with the vertical. All right, so here is our problem. Here is that rope connected to the ceiling, for example. We have an angle with the vertical this time, which is equal to 30 degrees. We know that the mass of this is 0.75 kilograms. And we know the radius of the circle, which is up here, is 35 centimeters. I want to know, first of all, what is the speed of the stone? Okay, so to do this, let's start by making our free body diagram. I would have the tension pulling it up and left and the weight. That is the free body diagram you would draw on a test. You would then have to resolve it into components. We know that this would be accelerating inward, which means that we would resolve the tension into components going up and in. It is not accelerating vertically, which means the y component of tension is balancing the weight, and the x component of tension is the net force. Okay, so the first thing I want to do is, in part A, is I want to figure out what is the speed. And I'm going to do that by using my net force equation, that the net force is mv squared over r. And that net force is the x component of the tension. That x component of tension is the tension, the x, would be opposite that angle. The x direction is opposite the angle, so that x component is ft sine of theta. Now, I don't know what ft is, but I got to figure it out. And I can figure it out using the fact that the y component of tension is equal to Fg. And the y component of tension is Ft cosine of theta in this problem. And the weight is mg. So the tension is therefore mg over the cosine of the angle. So that means I have mg over the cosine of the angle times the sine of the angle is equal to mv squared over r. Notice the mass of the stone is going to drop out. Sine over cosine is another trig function that you should be aware of. Sine over cosine is equal to tangent. So I have the tangent of the angle times g is v squared over r. So v would equal the square root of r times g times the tangent of the angle. So let's go ahead and plug in. R, we should know, is 0.35 meters. G is 9.8 meter per second squared. And that's the tangent of 30 degrees. So what is the speed of the stone? Well, just plug it in and solve. 0.35 times 9.8 times the tan of 30. Take the square root of that answer. And that gives me an answer of 1.41 meter per second with the 3 sig figs that the textbook would like you to come up with. Now in part B, it asks us for the tension in the string. What is Ft? What is Ft? Well, I can get it from this. The tension in the string is mg over the cosine of the angle. So that would mean I'm going to take the mass, which they told me is 0.75 kilograms, multiply it by 9.8 meter per second squared, and then divide by the cosine of 30 degrees. So 0.75 times 9.8 divided by the cosine of 30 gives me an answer of 8.49 newtons. Okay? And that's question 67. Anything else, Matt?
I have a question on I put my equation as ft sine theta equals mass times g.
But it doesn't, because the angle was given with the vertical. So here, the y side, your y side is adjacent to the angle. So you have to use cosine for any y value. Anything in the x would be opposite. Okay? So you had them backwards. Unless you use the complement. Sorry. So you use the complement of you use 60 degrees, that's fine. Should give you the exact same thing. Yes. Yes, let's look at 73. So 73 says a man is swinging his child in a circle that has a radius of 0.75 meters as shown in figure 557. If the mass of the kid is 25 kilograms and the kid makes 1 revolution in 1.5 seconds, what is the magnitude and direction of the force that must be exerted by the man on the child? So basically, they tell you, assume the kid is a point particle, otherwise you can't do this. So here is the kid in that question. There is a tension force being pulling him up and left, or up and right, excuse me, and the kid's weight directed downward. So we know that the kid is going to accelerate inward because they're moving in a circle at a constant speed, which means that we would resolve all of our forces into the parallel and perpendicular directions to solve this, which means that we're going to have a tension component in the y direction, a tension component to the right, and a weight pulling them down. The y components of tension are going to balance, and the x component of tension is our net force. Now, they tell us that the radius of the circle, which if I were to make a triangle here, let's do it like right here, that radius is 0.75 meters. And we know the mass of the child. We know the mass is 25 kilograms, and the period of revolution is 1.5 seconds. So I'm going to set this up very much like what we were looking for. So the force of the man on the child is the tension. That is the tension. We want to know, what is that tension force? So I have two equations I can use. First of all, in the y direction, the tension is balancing the weight. I'm not going to solve for an angle, but let's just put an angle somewhere in this question. Let's put an angle here with the horizontal this time, okay? So that means FTX would be the tension times the cosine, and the y would be FT times the sine. So the y component would be FT sine theta. That would have to equal mg. In the x direction, that tension is the mass times the centripetal acceleration, v squared over r. Now, that x component of tension is Ft cosine theta. I'm going to try to eliminate an angle, which I can do. So if I do that here, I would get that the angle is the inverse sine of mg over the tension. So I can plug that in over here. So I'm going to do the tension times the cosine of the inverse sine of mg over the tension. And this is going to get kind of ugly when I do it this way. So let's try to clean it up and make it a little bit easier. So that way I don't have this really ugly thing. So let's figure out what the speed is first. And I know I said save everything for the end, and you can. Do I want to get the angle first, like we were doing before? Why not? Let's first get our speed, because you can solve for that. 2 pi r over t. 2 pi times 1.5, 2 pi times 0.75 meters over 1.5 seconds. So you would get a speed of 2 pi times 0.75 divided by 1.5 gives us an answer of pi, 3.14159. It's pi. So the speed is just pi. Let's just leave it that way. It's pi. That way we don't have to round it. That's in meters per second. So to come up with my tension, let's actually get the angle first. So if I do that like I did before, this would be mg over the sine of the angle. So this would be mg over the sine of the angle times the cosine of the angle is m times that speed squared over r. The mass is going to cancel out. So g times the tangent of the angle is v squared over r. So I'm going to come up with my angle by doing the inverse tan of v squared g over r. So let's get that. V we just found to be pi. So we're going to square pi, multiply it by 9.8, and divide by 0.75. So let's do that. And then I can take that angle, plug it in over here to get the tension. So if I do that, so second tan pi squared times 9.8 divided by 0.75 gives me an angle of, that doesn't make sense. Yeah, you're right. Or G over tan theta. Let's do that. G over tan theta. So that means, thank you. It is inverse tan of R over V squared G. So just flip it. Since I made that algebraic mistake. R, which is, thank you, 0.75 over pi squared times 9.8. Let's do that again. Second tan of 0.75 divided by the quantity pi squared times 9.8. That doesn't make sense. No, my math isn't working out here. So G over the tan is V squared over R. So tan theta V squared is RG. So tan theta is RG over V squared. That's what I'm going. Okay, the number's not working out. So this is inverse tan of RG over V squared. There we go. All right. So second tan of 0.75 times 9.8 divided by pi squared gives me, there we go, 36.6754497.8 degrees. I'm not going to round it. I'm just going to keep that in calculator memory to now give me my tension force by doing mg over the sine of that angle, where the mass is 25 kilograms, G is 9.8, and then I'll divide by the sine of that angle right there. So if I do 25 times 9.8 divided by the sine of the previous answer, that gives me a tension force equal to 410 newtons. Okay. Emma, does that make sense? Once I got my algebra right. But I'm looking at my answer on the calculator. My angle with what I was doing before was 0.44 degrees. I'm like, I know that's not right. So where's my mistake? It's back in the algebra. You always go back, find your mistake, and fix it. Okay, anything else? Okay, then for tomorrow. Tomorrow's Wednesday. It's the last textbook assignment for this chapter. Assignment 26, which has 7 questions. They are questions 83, 86, 88, and then 92 to 95. 7 questions total. For Thursday, there are 22 videos that you should have been working on watching to get you ready for that as you work on the next lab. You're all laughing at me. I posted those like 4 weeks ago. As soon as you did your other test, as you watched the other ones, they showed up. So, you're in a college class. You can't expect that I'm giving you I could give you everything for the rest of the year. And now you just have to manage your time to get things done, because that is what a college professor would do. Day 1 of the course, they're going to tell you, here is a list of all the assignments for the year. or for the semester. Good luck. So they've been posted for at least 3 weeks, which means you should be looking ahead and trying to figure out how you're going to manage your time, knowing that you are going to be asked to watch videos, and there's lots of them. This is a huge part of the AP course, chapters 4 and 5. So there's lots of little videos that will help you, should be helping you as you go along. Waiting to the last minute to watch them means I know you're not watching them. You're just hitting play and watching, like, you got 6 videos all going at the same time, so you're just getting the video credit. Believe me, I'll know it when you take your test. I'll know it because you're not doing the review. You're not doing it the way you need to. Okay? Anytime we do labs, videos are due. So when you have labs coming up, know that those are videos when you're collecting data. That's how it's done all year. Just a heads up, in case you haven't figured out that pattern yet. All right, so you got a minute here, probably not enough time to get started, but don't just be working on homework problems.